Before I talked about the different kinds of errors that we can make. This is a useful table for discussing types of error, and we could have a situation where H0 is true and we accept it, in which case we make no error, or we could have a case where H0 is false and we reject it, in which case we make no error. But the type 1 error and the type 2 errors are shown in this error table. Hypothesis tests on the mean of a distribution may be one-sided or two-sided. If we're making a two-sided hypothesis test, then our null hypothesis is always the mean is equal to some particular value that we want to test, against the alternative hypothesis that the mean is not equal to that value. We aren't making a distinction about whether it's above or below that. We're just saying it's not equal to what we thought it was. We might also take on a one-sided test where we would be making the assertion that the mean is greater than or equal to some value mu 0, or that the population mean lie is less than or equal to some particular asserted value. In each of those, we would have the corresponding alternative hypothesis that no, it's not greater or equal, or no, it's not less than or equal. So notice that in each one of these, when you look at the case of equality, that equality exists always in the null hypothesis. So you could never have an alternative hypothesis that says less than or equal to or greater than or equal to. The alternative hypothesis is always does not include the possibility of equality. What are some of the assumptions for a t-test? The number of observations in our sample is given as the value n. If n is less than 30, the data should be more or less normally distributed, or you shouldn't conduct a t-test. If n is greater than or equal to 30, the central limit theorem, which is introduced in your text and which I mentioned in the last chapter, then the central limit theory applies, and we can go ahead and use the t-test. So if we have a large number of observations, then we know we can use a t-test. If you have a relatively small number of observations, less than 30, then you've got to be sure that you have a more or less normally distributed data set. If we're looking at the two-sided t-test on the mean, it involves n observations with sample parameters x bar and s, and we identify the null hypothesis and the alternative hypothesis. We then must select the level of significance and set up the problem. And when you conduct a hypothesis test, you should always write it in the exact same form. You should state what your level of significance alpha is going to be, should write down what your H0 is, write down what your HA is, your alternative hypothesis, then calculate the test statistic, in this case the t statistic, and there's one way of writing the equation for t. Then you need to find the t critical value. So using n minus 1 degrees of freedom, find the t critical for the value using 1 minus alpha over 2. And you use 1 minus alpha over 2 because in the two-sided case, and that's what we're discussing here, we have to consider both the upper tail and the lower tail, so we have to allow half of alpha in each tail or each side of the tails. And if your absolute value of t is greater than t critical, then you reject the null hypothesis in favor of the alternative hypothesis. Or if the absolute value of t is less than the critical value, then you have no reason to reject the null hypothesis. The way I always say that this is because we're always setting this up with a null hypothesis and alternative hypothesis. If you're rooting for the null hypothesis, a large T is bad for the chances that we'll accept H0. So big test statistic tells you that you're probably wrong about your assumptions about the mean. We also will be looking at one-sided t-tests on the mean. And here we have our null hypothesis may be that our population mean is greater than or equal to some hypothesized value, mu sub 0, against the alternative hypothesis that mu is actually less than that hypothesized value. And we need to pick our level of significance, calculate the test statistic. Using n minus 1 degrees of freedom, we find the t-critical value using 1 minus alpha. Notice we don't have to allow it to be 1 minus alpha over 2. We only worry about one tail in this case. In this case, if our absolute value of t is greater than or equal to t-crit, then we reject the null hypothesis in favor of the alternative hypothesis. If absolute value of t is less than the critical value, then we'll have no reason to reject the null hypothesis. The other one-sided t case would simply reverse the greater than or equal to a less than or equal to in the null hypothesis, which means the alternative hypothesis must also switch the direction of the sign. But we calculate the t statistic the same. We look up the number of degrees of freedom in the same way. And we reject our null hypothesis in the case of a t of large magnitude, and we have no reason to reject it in the case of a t of magnitude less than t critical. In the last section, we learned about confidence intervals. In this section we learned about hypothesis tests, but these are actually very closely linked. In the same way that you might conduct a two-sided hypothesis test, you could have calculated a two-sided confidence interval. If you're going to end up accepting the null hypothesis, your hypothesized mean will lie somewhere inside your confidence interval. And if you're going to end up rejecting the null hypothesis, then your hypothesized mean will lie outside the confidence interval. So in fact, if you calculate a confidence interval, you'll be able to immediately know how to interpret the result of a hypothesis test, because these two actually will tell you the same thing. So if your hypothesized mean lies within your confidence interval or bound, then you'll have no reason to reject your null hypothesis. But if your sample average lies outside a confidence interval, then you're going to end up rejecting that null hypothesis. These are probably easiest to see in some of the applications, and I've included several in this section. We sometimes make a hypothesis test using the z-test, and this is appropriate only in the case of a known variance or known standard deviation to the underlying distribution. Sometimes we do get to know a particular type of data or particular type of variable or particular data set so well that we have enough confidence to assert that we know the that we know the standard deviation. But more commonly we don't, and we have to use the t-test. But if we do know it, then you can calculate the z statistic instead of the t statistic. But otherwise, the hypothesis test is the same as it was in the previous slides.